Hello everyone, and welcome back to Educator.com. I'm Dan Fullerton, and in this lesson we're going to talk about conservation of linear momentum. Our objectives include explaining how linear momentum conservation follows as a consequence of Newton's third law for an isolated system, identifying situations in which linear momentum is conserved, and applying linear momentum conservation to situations in which two or more objects interact to solve a variety of problems. So let's talk about conservation of linear momentum. In an isolated system where no external forces act, the total linear momentum of that system stays the same. It must be conserved. Now, in that closed system, that means the total linear momentum is constant. Whatever you have before some event must be exactly the same as the total linear momentum you have after that event. That's a direct outcome of Newton's third law of motion. When you have a force of object 1 on object 2 exerts the exact opposite force, same in magnitude, opposite in direction on force 1, which maintains that amount of linear momentum in that closed system. So, collisions and explosions. In the case of a collision or explosion, if you add up the individual momentum vectors of all the objects before the event, and then you compare that to the sum of all the momentum vectors of all of the objects after the event, you'll find that they are the exact same. Written mathematically, the law of conservation of linear momentum states that the initial total momentum equals the final total momentum. So how do we solve momentum problems? First, identify all the objects in the system. Then determine the momenta of the objects before the event and use variables for any characteristics you don't know. Determine the momenta of the objects after the event, again using variables for anything you don't know. Add up all the momenta from before the event and all the momenta after the event and set them equal to each other. The law of conservation of linear momentum says they have to be equal, and then you can solve for any unknowns. Now, when we talk about collisions, there are two main types of collisions. An elastic collision is a collision in which kinetic energy is conserved. The kinetic energy before the collision is equal to the kinetic energy after the collision. That's a bouncy type of collision, for example. And there is no law that says the kinetic energy before a collision has to equal the kinetic energy after the collision. That is not always the case. However, if it is the case, we call that an elastic collision. And an inelastic collision is a collision in which kinetic energy is not conserved, a sticky collision. The two objects stick together. And you have various levels of things in between, partially inelastic collisions, things like that. But the key thing you need to know, if something says it's an elastic collision, the kinetic energy before equals the kinetic energy after. Let's do an example of a traffic collision. We have a 2,000 kilogram car traveling 20 meters per second, and it collides with a 1,000 kilogram car, which is at rest. If the 2,000 kilogram car has a velocity of 6.67 meters per second after the collision, find the velocity of the 1,000 kilogram car after the collision. Well, the way I like to solve these is with a momentum table. So let's start by labeling our objects. This 2,000 kilogram car, let's call it A, and the 1,000 kilogram car, let's call it B. Then what we can do is we can make a table to organize our information. We'll have a column for our objects. We'll have a column for the momentum before the collision in kilogram meters per second, and a column for the momentum after the collision, P after, in kilogram meters per second. And since this is in one dimension, we don't have to worry about X and Y, Z components. It's all one dimension. So let's make ourselves a nice, happy little table. And our objects, we have car A, we have car B, and we'll make a row for total. Just filling in lines on our table to help us stay nice and organized. And for car B, and that should work. All right, filling in what we know. Car A is 2,000 kilograms traveling at 20 meters per second before the collision. So its momentum is mass times velocity, or 2,000 times 20, which will be 40,000 kilogram meters per second. Car B before the collision is at rest, so its momentum is 0. So our total momentum before the collision is 40,000 plus 0, or just 40,000 kilogram meters per second. Now, after the collision, car A still has the same mass, but its velocity is 6.67 meters per second. So its momentum after is 2,000 times 6.67, or 13,340 kilogram meters per second. The momentum of car B after the collision, well, its mass is still 1,000, but we don't know its velocity, so I'll put a variable in there, VB, for its velocity. So its total momentum after is just 1,000 VB. And if I find the total by adding those up, I come up with 13,340 plus 1,000 VB. Now we apply the law of conservation of momentum, which says that the total momentum before the collision has to equal the total momentum after the collision. We do that by just stating that our totals here must be equal. A little bit of algebra. 40,000 equals 13,340 plus 1,000 VB. Let's subtract 13,340 from both sides. And I have that 26,660 must equal 1,000 VB. Therefore, VB must equal 26 and we'll round that to 26.7 meters per second. So there's the velocity of car B after the collision, applying law of conservation of linear momentum.